Hello everybody. So now we'll be talking about purely inductive circuits. Earlier we talked about purely resistive circuits. Now it's turn for purely inductive circuits. So the question arises, what is an inductor? Okay, so here I have connected an AC source which is providing an EMF as a E naught sine omega t plus phi to this inductor. So as I was saying, the question is, what is an inductor? So inductor is basically a current carrying coil only. It's like a conducting wire which which is insulated, and it has many turns. So the wire doesn't create any problem for current to flow. The problem occurs because since there are turns in this coil, and when you apply AC on this coil, the current passing through this coil keeps on changing. As a result, the magnetic flux which this coil creates around it also changes. And when the magnetic flux will keep on changing, it will provide a resistance to that change, and that resistance is indicated by inductance of the inductor. So what I'm saying is that the magnetic flux which you call as phi equal to B dot A is further associated with inductance of this coil and the current passing through this coil. As I change the current passing through this coil, the flux through this coil also changes, d phi by dt. And from the previous chapter of EMI, we know that EMF generated is basically minus of d phi by dt. Yes, so basically minus L di by dt. This is the EMF generated across the inductor coil when the current passing through it changes. So I know the EMF across the inductor coil. Now when I apply an EMF E on this inductor using this AC source, so my as per Kirchhoff's law, voltage law, E is the applied voltage minus L di by dt, this is the voltage drop across the inductor, is going to be equal to 0. Now E can be put this side, L di by dt is coming this way. I'll do the integration. E dt is here, L would come in the denominator, di is here. I can integrate it. Now I can integrate it over a complete cycle, but the problem is it would give me the total charge passing through the inductor coil in one cycle, which is again going to be in the cyclic form. Yes, it's going to be in the cyclic form. So the problem is that I myself know that the integration of this over the limit 0 to t is going to be 0 only. Why? Because the average current over one complete cycle is going to be 0. So I just need to get an expression for the current. Okay, so I'll just write it as I, which will be a function of time. And then if I'll put for the values here, I'll get E upon L. E can be replaced as E naught sine omega t plus phi and dt. Yes. So now let's integrate it. E naught upon L can come out because it's a constant. Then sine integration of sine will be minus cos omega t plus phi, and then the denominator it would be omega t. It would be omega only, not t, and this is your function of it. So this is what I got, it as E naught upon omega L cos omega t plus phi, and there's a minus sign here. See, earlier the phase that we have got for EMF, it was E naught sine omega t plus phi. It was a sine function. Here it's coming out to be a cos function. So I need to find a way in which I can convert this cos into a sine function. So let's do it. Omega L if I write this cos function as sine pi by 2 minus omega t plus phi, it's again going to be this way. Yes. Now what I'm going to do, I'll bring this minus sign inside, and it would give me omega t plus phi minus pi by 2. So I've got the expression for current as this. Yes. Now in this expression, if I start to relate it with the basic expression, with the peak value of the current, see, I know this is a constant, E naught by omega L. So if this is a constant, this is going to be equal to I naught, which is equal to I naught I is equal to I naught sine omega t plus phi minus pi by 2. Yeah, this expression, and this extra minus pi by 2, which we are seeing this. I naught here is E naught upon omega L. This is the peak value of current, which is coming out to be dependent on omega. Peak value dependent on frequency. Now this, what to do about this minus pi by 2? What does it indicate? My EMF expression is going this way, whereas my expression for electric current is this way. It's a little behind this. Can you see? It's far, it's ahead, but this phase omega t plus phi is minus pi by 2. It's reduced by a factor of pi by 2. Means if I would have my current, if I have my EMF shown up like this, let's suppose let phi equal to be 0 for a while. Initial phase को 0 मानते हैं. So my EMF is going to be, let's say E naught is this. It's like this. So this is minus E naught. Now what does this minus pi by 2 say? It says that if my EMF has gone far off, my current is still behind by a factor of pi by 2. Now what does it mean? In one complete cycle, like in t time period, a varying quantity like EMF or current covers 2 pi phase. These are the vibrating quantities, right? Here EMF is vibrating and correspondingly current is also vibrating. But in a cycle of 2 pi, the vibration happens this way, that the value starts from 0 value, reaches to its maximum, again comes to 0, then goes back in the opposite direction, and then again becomes 0. So this is how my EMF and my voltage is vibrating. In one complete cycle, the vibration, or I would say, as you have studied in earlier, this is related with your SHM, and SHM being a projection of uniform circular motion on the x-axis or y-axis. So as I said, this is your omega t, and this is how how is the projection varying. So if this is the cos function, this is your sine function. So you can consider this one. So in one complete cycle, in 2 pi, in one complete cycle of time period, it would cover an angle of 2 pi. Yes, this vector, this is basically your what? It can be I naught or E naught. Let's say it's E naught. So in one time period, it's covering one complete phase, 2 pi. Yes. So t equal to 2 pi. So let's suppose if I have to talk about this t by 4 pi by 2 time, how much will it be? See, if it starts from here and goes till here, it would be a time corresponding to t by 4. Means if my EMF is here at this point, the value of current will be behind by t by 4 factor. Means here is the T by 4. Here the value of EMF is 0, but the value of current will be this maximum. And when my EMF will become maximum, my current will become 0. So it's like that. And when my EMF will become, so the problem is that I have taken the amplitudes to be same. Let's say this is the value of my E naught upon omega L, that is I naught. It's negative, and it should also be from here. And this is your I naught plus. So when my EMF is at the max, is at 0 value, at t equal to 0, the current is at minus E naught upon omega L. And then when my EMF is at maximum value here, the current has become 0. And the next part, in the t by 2 part, when the EMF has gone to 0 value, the current has reached its maximum value. And again, if you see, when the EMF has become maximum in opposite direction, at that time the current is taking the minimum value. So you can see the current is lagging EMF. EMF is running faster and current is behind it. This is how this works. What I'm saying is, let me make another diagram here. So the only mistake I've done with the previous diagram is I've taken the amplitudes of EMF and voltage to be nearly same. So I'm just changing it so that it's more understandable to you. So here is, let's say this is my E naught and this is my minus E naught, and this is I naught and this is minus I naught. So if at t equal to 0 my EMF reaches its maximum value like this, then reduces, then goes in the opposite direction, and this is how the cycle has completed. So what happens to current? It's behind by a factor of pi by 2, by a phase of pi by 2, which is corresponding to a time interval of t by 4. Yes, because आप देख सकते हैं 1/4 of the cycle is completed in t by 4 time. So if it's far off by t by 4 time, so what will happen? This is t by 4, this is t by 2, this is 3t by 4. I'm dividing the cycle, complete cycle, in 4 parts. This is your t. Now if it's behind by t by 4, which means when my EMF is 0, then my current has to be maximum. And when my EMF will become maximum, the current has become 0. And then when my EMF has become 0, the current will reach only this way. And when my EMF has gained the maximum value in the opposite direction, at that time my current will gain a value of 0. Similarly, when my EMF becomes 0, then my current becomes maximum in the opposite direction. So this is how, this is the phase difference of pi by 4. Phase difference, pi by 4, not pi by 4, it's pi by 2. And you can say current lags the EMF in inductor. Okay, so this is the maths behind it, and you got the result, and you can see you might need to produce it in the exam, so it's quite an important thing. You focus on this diagram, it's better one because it has both the magnitudes specified differently. Yes, thank you. Now let's come to capacitor. Okay, now we'll do some work on capacitor. So basically What kind of circuit? Purely capacitive circuit. So what I'm doing, I have this AC source. Oh, I mistakenly placed it here. So we are making an AC source, and I'm placing a capacitor here, about which you have studied in electrostatics. AC source again providing an EMF of E naught sine omega t, and capacitor. What is a capacitor? Two plates which store electric field in the electrical energy in the form of electric field, right? Now, as the polarity of this AC source will keep on changing, the direction of field across this capacitor will keep on changing. In the first cycle, it would be plus here, minus here, so field would go along this, and in the other cycle, plus would come here and minus would come here. So field would go this way. So this would keep on happening. In each cycle, the direction of field would change across it twice. Okay, so as a result of it, even the capacitor is going to provide some kind of resistance. Just before now, we studied about inductor. So here I had mentioned this E naught term, but there is this omega L also here. This omega L tells me something. This omega L is basically creating a kind of resistance for the change of magnetic flux across the inductor. So this is called as inductive reactance. ये resistance, इसका its behavior is just like resistance. However, resistance used to be against current, but this inductive reactance is against the change in magnetic flux across the inductor. The magnetic flux change is happening due to change in current, and this change in current is basically the property of this external AC source. However, this inductive reactance is the property of this inductor, that it doesn't want the change to happen. So here this factor, inductive reactance, is dependent on this external frequency of AC, कि AC कितना किस फ्रीक्वेंसी का है, और उसके अलावा दिस इज ऑल्सो डिपेंडेंट ऑन द प्रॉपर्टी ऑफ द इंडक्टेंस, कि हमारा इंडक्टेंस कितने टर्न से बना है, कौन सा मटेरियल इंडक्टर के बीच में रखा है. मतलब इफ़ वी प्लेस सॉफ्ट कोर द थिंग्स वुड बी डिफरेंट, and number of turns and everything this is dependent on. So this is what is behaving like a resistance in case of inductor. Now we'll see another such thing in the case of capacitor also. When you will do the further analysis using integration and all, you will get another expression which would indicate how the capacitor behaves, or I would say goes against the change in electric field that is occurring due to this EMF. मतलब इस EMF के चेंज की वजह से कैपेसिटर के अलॉन्ग जो बार बार इलेक्ट्रिक फील्ड का चेंज हो रहा है, उसके अगेंस्ट कैपेसिटर कैसे बिहेव करता है, और उसके अगेंस्ट कैपेसिटर किस तरह की रेजिस्टेंस प्रोवाइड करता है. सो लेट्स डू दिस. वी हैव स्टडीड दैट कैपेसिटेंस इज इक्वल टू is a ratio of Q upon V. Yes, so Q is equal to CV. So if Q is this and V is my applied voltage, which is E naught sine omega t, I can do this thing, that I can make it dQ by dt. I can take this derivative so that I get an expression for current. So I get C epsilon naught sine omega t, derivative is cos omega t, and I'll apply chain rule. So omega t is also a function of t, so I'll get omega also. So I'll get E naught C omega cos omega t. This is my I as a function of time for the capacitor. It is coming out to be C omega epsilon naught cos omega t. Now again, my EMF was a function of sine. Here I am seeing a cos. So let me convert this cos into sine so that I get a relation between the phase. how the sinusoidal function of EMF is changing and how the sinusoidal function of current is changing. In the case of resistive circuit, you had seen that both were going together. E naught sine omega t was for EMF, for the voltage, and I naught sine omega t was for the current. So they were both in the phase. They were both running at the same speed. But here the things are going to be a little different. So if I have this E naught here, and cos I can convert, I'll write it as sine pi by 2 minus omega t. It would be cos omega t, right? And then here I have this omega c, which I can bring in denominator and make it like that. This is my current. Now if I have to see this, and this is the case of capacitor, I have to see, as if you see for some trigonometry, you will find that sine pi by 2 plus theta is also cos omega t, because in second quadrant, it's like all school to college if you have studied about that in first quadrant all ratios are all ratios are positive. In the second quadrant, sine is positive, and in the third quadrant, tan is positive, and in the fourth quadrant, cos is positive. So if that's the case, the cos omega t can further be written as sine pi by 2 plus omega t, because sine 90 plus theta will come in this quadrant where sine is always positive, and since there is a pi by 2 here, it will convert into cos. So you can see I got a new expression which has E naught sine pi by 2 plus omega t, and there's 1 by omega c here also. Now if this is the case, I need to see how has my expression changed. So I have got IT as something where just a second, this is my pi by 2 minus omega t plus omega t. I have got I naught as something which is E naught upon 1 by omega c. Yes, and I've got the function IT as such that it is pi by 2 ahead of omega t. If my EMF is at omega t only, is EMF has a phase of omega t, my current has a phase ahead of omega t. It has pi by 2 factor added. So if I'll draw a diagram, an IT and VT diagram to show the variation, let's see how it happens. This is 0. I'm taking the initial phase phi to be 0, the way I did earlier. Here also, here I didn't take the generalized case from the starting. You can take it, it's not going to bring any big change. And now here I put, let's say I put E naught 1 by omega c. This is my I naught, and this is my E naught. Similarly, this is my minus I naught. This is also equal to I naught, and this is minus E naught. So let's see how it happens. It's E naught sine omega t, means my EMF starts from 0 and goes to its maximum value in t by 4 time. This is my t by 4 time. Then in t next part, it reaches to the minimum value. Then it goes in the opposite direction and reaches a value, maximum value in the opposite direction. Here the time is 3t by 4, and if I'll go this way, I'll find it. In t cycle, it has completed the cycle, reaching from 0 value to maximum, then to 0, then minimum, then the value, maximum value in the opposite direction, and again to 0 value. So this is how it has completed its cycle. Now I see my current having a phase omega pi by 2 more in comparison to omega t. So as I said, in 2 pi cycle, 2 pi phase, t time is required. So for pi by 2, we would require a time of t by 4. Yes. So if that's the case, being ahead by a factor of pi by 2 means running ahead by a factor of t by 4. So if my EMF is 0, this means my current will be higher. Current is higher, and then my current would start reducing. Means when my EMF was 0, my current was maximum in the forward direction. When my EMF became maximum, my current turned 0. Then when my EMF turned 0, the current increased to a value of my maximum value in the opposite direction. Then again, when my EMF became maximum in opposite direction, my current turned 0. And then when my EMF was 0, the current was maximum. So here we can see that current is running faster in comparison to EMF. EMF is running behind. It's 0, but still the current has increased to maximum. Then current starts reducing, EMF starts increasing. The cycle is going pi by 2 by a factor of pi by 2. Yeah. So here capacitor, you can say, you can keep it in mind also. In capacitor, current leads voltage. And here the one of the beautiful thing is, see, I'm trying to make an analogy just like the way we did for inductor. In case of resistor, we have I naught equal to E naught by R, if we remember. In case of inductor, we had something like I naught equal to E naught upon omega L. And in case of capacitor, I get I naught equal to E naught upon 1 by omega C. So here, these things are omega L, 1 by omega C. These are coming at same position if we try to relate them. They are inversely proportional to the maximum value of peak current. So this indicates that they have nearly same nature. It's resistive, opposes the flow of current. Then this is omega L. This is your inductive. You don't call it resistance. We call it inductive reactance, because it is not against current. It is against the change in current. Inductive reactance, change in current. It's against that, because if current would be changed, magnetic flux would be changed, and then inductance would come in picture, because it doesn't want the change to happen. Then we have 1 by omega C. This is my capacitive reactance. Why this is occurring? Because this is against change in electric field. It doesn't want the electric field to change. And electric field is changing because of EMF. So it is not EMF, voltage, I would say. So this is against voltage, a change in voltage. This is against the change in current across the inductor coil, and this is against the change in against current only. It's not against change in current. It's against current. Why current is flowing? It doesn't want. It acts as an obstacle. So you can also see here's a resistive material that we use, a material little different. Nichrome wire we use. At times we use constantin and magnin and many other alloys which have high resistance, which obstruct the flow of current. But in this case, inductor, we don't have a resistive material. We have a conducting material turned into form of coil, so that it can store some magnetic field, and the change in that magnetic field creates kind of impedance, or I would say a reactance, a kind of a resistive nature, but it's not same as resistance. That's why we have mentioned it. That's why we have given it a different name. Resistance case can occur for DC, and resistors behave the same way for DC as well as AC. But inductors behave differently because they have a factor of frequency involved. सो फ्रीक्वेंसी पे वो डिपेंड करते हैं और फ्रीक्वेंसी डिसाइड करेगी कि वो अपने अंदर से करंट को पास होने मतलब दिस वेरिएशन दे अलाउ द सर्किट द AC टू फ्लो थ्रू इट और नॉट. Similarly, capacitor also depends on the frequency of the external source that we have provided. So that's why, since they are frequency dependent, we have given them a different name, which is reactance, not resistance. So in the final words, let me just talk some more about inductive, capacitive and resistive circuits. So resistance, you know that resistance is R, whereas inductive reactance is XL, denoted by XL, which is equal to omega L. And then third is your capacitive reactance, which is your XC, which is 1 upon omega C. So the factor to be noted is R, independent, just a second, independent of the frequency of current. So if it's not dependent on the frequency of current, so same for AC and DC circuits. Whatever be the kind of circuit that we are using, it's going to behave the same way. However, when you go for inductive circuit, you see XL is directly proportional to omega. Means higher the frequency of the current, higher is the impedance, inductive reactance. High frequency, higher impedance. And higher impedance means I naught की जो वैल्यू थी वो थी E naught upon XL. Then if this would increase, this would reduce. पीक वैल्यू कम आएगी. जितना ज़्यादा फ्रीक्वेंसी चेंज हो रही होगी करंट की, इंडक्टर उतना कम पीक वैल्यू देगा करंट की, उतनी कम पीक वैल्यू सर्किट में से पास करेगी. Then another is this case where if I say omega is inversely proportional to XC. Yes, so if omega increases, means frequency of the current increases, XC reduces, and if XC reduces, my I naught is E naught upon XC. So if XC reduces, I naught is going to increase. So higher frequency here, lower impedance. आप impedance word नहीं यूज़ करना चाहते, you use the word reactance. Impedance अभी हम पूरे combinational circuit के लिए यूज़ करेंगे. So lower reactance, higher frequency, lower reactance, and a lower reactance means higher current, higher value of I naught. और इसमें higher frequency, higher impedance, lower peak, lower value of I naught. So this is how the three components are going to control the device. Capacitor depends on frequency. Yes, you can see the capacitive reactance dependent on frequency. Now see, if omega is 0, when does it happen? Omega is 0 in case of DC. So if omega is 0, the XC is going to be equal to 1 upon 0, which is equal to infinity. Means capacitor will provide infinite reactance, so no DC will pass. So capacitor would start behaving like a switch. It won't allow the current to pass through it. Okay. So, and if you see the case of inductor, if omega is 0, see, if omega is 0, like if you are providing DC to inductor, what happens? Direct current to inductor. In that case, your XL will turn out to be 0, because आपने देख लिया कि XL equal to omega L, so it will turn out to be 0. And when it would be 0, your value of I naught will turn out to be E naught upon 0, which is infinity. So inductor provides maximum current to to DC. Like you can pass direct current through inductor, it won't create any such problem. So it would behave like if it has become a highly conductive circuit, it has become like a highly conductive circuit, और एक तरीके से आप कह सकते हैं शॉर्ट सर्किटिंग हो जाएगी. DC के केस में अगर आपने इंडक्टर लगा दिया तो इट वुड कॉज शॉर्ट सर्किटिंग बिकॉज देयर इज़ नो रेजिस्टेंस. दैट्स वाई current is becoming infinity. So these are very important crucial cases they ask you in exams, so be ready with them. Thank you. In the next video we'll talk about LCR circuit and we'll see how the presence of inductor and capacitor together make the circuit along with the resistor make the circuit purely resistive and make it work more efficiently and can be useful for the case of radio and many oscillating circuits. Thank you.